In today's class, we will be starting our new concept, which is graphs. So, what is the definition of graph? A graph is a set of vertices and edges. So, it is just considered as a set of vertices and set of edges. So, we can just get G is equals to vertices and edges. So, if a graph is a collection of vertices and edges, then what are vertices? What are edges? So in tree we have seen, right, like this we will be having. So basically this part which we see it as node, that is called vertices. So let's take an example of a simple graph. Let's consider this cyclic graph in which A is a vertex and the connected lines is the right. These lines are called edges. So in this graph, what are the list of vertices? A, B, C, and D. These are all considered as vertices. We can call it as vertices or else nodes. Okay. So if you want to continue with the nomenclature of trees, you can just say it as nodes. What do you mean by edges? Edges. What are all the edges we are having here? AB is one edge, which is this edge, which is this edge. Next AC, which is this edge. Next BD, which is this edge, and lastly CD, which is this edge. So in this graph we are having four vertices and four edges. So if you got the concept, I will just write a graph example here. You want to say me how many vertices are there and how many edges are there. You just have to give me the count of it. Okay, so V is this, E is this, V is 4, E is 4, like that. You don't have to list them. You just have to give me the count of them. Okay, so this is our graph. Give me the number of vertices and give me the number of edges. So Adarsh is saying 6 vertices and 8 edges. Okay. So 1 vertex, 2 vertex, 3, 4, 5, 6. The number of vertices are 6. That is correct. When it when it comes to edges, 1, 2, 3. AB, AD, AB, AD, AC, 3, 4, 5, 6, 7, and 8. So edges is number 8. That is also correct. So guys, you guys got the concept of vertices and edges, right? You know if we you know that if a graph is given, how many vertices are there and how many edges are there and what are those things. If you got the concept, we will just move towards next concept. So if you got it, just you got it. Yes. And guys, when we come to trees, right, trees is also considered as a graph itself. So that is like one kind. So in this way, if we just collect this, add this, so this becomes graph. And if you keep it like this only, then also it is considered as a graph. So we will be having so many questions in graphs where our structure will be like this only. Okay, so don't get confused between trees and graphs. Like you don't have to like separate it, and if you got it like this, there is something else. If you got it like this, there is something else. No, it's all depends on your logic. When the topic gets complex, right, then it relies on logic fundamentals. That's it. Our next topic which we are learning is next concept which you want to know is undirected graphs. So basically, whatever you know about graph till now, which I have covered, I have shown you guys undirected graph. So let me just give an example of it. I will not explain it. I will explain it when I will explain the next concept. So our next concept is directed graph. These are few terminologies which you should know before solving graph concepts. So that's why we are seeing this thing. Directed graph means assume we are having same set of edges, but here we are having directions. At that time, it is called as directed graph. So here from A we can go to D, we can go to B. This is by undirected, right? But here from A, here in this particular example, we can go to B also, we can go to D also. But when it comes to here, let's take an example of C. Here from C we can go to even go to B and even go to D. But here from C we can just go to D, we cannot go to B. And one more thing you guys should know is neighbors. Okay, what do you mean by neighbors when it comes in real world scenarios also? Whoever are residing beside you, so who are residing left to you, who are residing right to you, they are called neighbors, right? Similarly, neighbors of A in this example would be D and B. So basically, they from A we can go to D, we can go to B. That's why we will call them as neighbors. So here the neighbors of C would be only D because we can't go to D and E. So from C wherever we can go, what are the neighbors that we will consider them as neighbors. So from C we can go to A because from C we are having a direction. From C we are having this direction also. We can go to D. But from C we can't directly go to B, but we can go to A then go to B. That is different case scenario. But at that time B is not considered as a neighbor because it's not directly connected, right? So whenever it is directly connected in our undirected graph, adjacent nodes are only called as neighbors, but here we just have to see it, the directions, and then write the neighbors. I hope guys you understood this concept. This is just a simple thing. So next we will move to complete graph. So what do you mean by complete? For example, all vertices in a graph should be connected with each other. So for example, if we are having 5 vertices in a graph, each of these 5 vertices should be connected to each other. Let's take, we are having 4 vertices A, B, C and D. So A should be connected to B also, A should be connected to C also, A should be connected to D also. Likewise, B should be connected to A, we have already connected it. B should be connected to C, B should be connected to D. Likewise, C should be connected to A, B and D. Likewise, D should be connected to. So in a graph where all the vertices are connected to each other, at that time we will call that graph as complete graph. Okay. Next one is weighted graph. What do you mean by weighted graph is, so till now what we have seen, each and every edges are like common edges. But if we just add weight to them, if we add meaning to those edges, at that time that particular graph is called as weighted graph. Let me give you an example. For example, let's call it, well, let's add a weight of 2. Let's call it 1, 3, 4, and 8, like this. Okay. So we have just added weight to each edges of a graph. Why it is used, what is the real world scenarios of using it is, you can see in map, right? In map, if you want to go from A to D, so suppose A and D are two cities, and you can go from A to D using this. Okay, let me just erase this. Okay, so one path is how you can go from A, you can go to B. From A, you can go to B. From B, you can go to, what is this? C. C. From C, you can go to D. A to B, B to C, C to D. This is one path. Next path is you can directly go from A to C. C. I'll just change it to 2, just to give you a reference. Okay, A to C, C to D. A to C, C to D. This is one path. Next path is A to B, B to D. A to B, B to D. Next path is A to C, C to B, B to D. A to C, C to B, B to D. Okay, now let's just consider the weights. Like let's say here weight representing the kilometers. Okay, not don't go like logical wise. Just consider these are the distances, or you can say this is the amount of rupees which we need to travel. So from A to first one is A to B. So for traveling A to B, we need 1 rupees. From B to C, we need 2 rupees. From C to D, we need 4 rupees. So 4 plus 2 plus 1, this is 7. We will be needing 7 rupees to follow this path. Let's see this path ACD, A to C, C to D. For this, we will be needing A to C to C to D 4. So we will be needing 6 rupees. Next ABD. ABD means A to B 1, B to D 8. 8 plus 1, 9 rupees. Let's say ACBD. A to C 2, 2 to B 2 again, which is 4. 4 to 4 plus 8, 12. In this path we will be spending 12 rupees. At that time, which is the convenient path, or what we can say, which is the shortest path, which or minimum cost path, like that. So at that time we will consider which is the least one, which is having the least one, that which is 6. So this is the shortest path. Like this we will use the weighted graph. In our maps also we will use the same concept. At there we will use the algorithm, the zigzag algorithm, or other minimum spanning algorithms, like that. We will learn those algorithms also in our future classes sessions. For now, I want you guys to know what is weighted graph and how we will do it. That's it. Next, what you have to know is degree of a vertex. So, what is degree of a vertex? Degree of a vertex is considered as total number of edges linked to that vertex. For example, let's consider we are having a graph A to B, B to C, C to D, D to E. Okay, so let's consider this is our graph. We'll add this also for aesthetics. So in this graph, what we have to write, we have to see, we have to find the degree of A, degree of B, C, D, E. Okay. So I'll say the degree of A and B. You guys will say the degree of CD. What is the degree of A? Is the total number of edges linked to that vertex. So for A, how many edges are attached, linked? One edge, two edge. So what is the degree of A? 2. Similarly, for B, how many edges are attached? 1, 2, 3. At that time, degree of B would be 3. Likewise, give me the degree of C, D, and D. Ananya said 3, 2, and 4. Let's just see. So when it comes to C, 1, 2, 3. So and this answer is correct. When it comes to D, 1, 2. So this answer is also correct. When it comes to E, 1, 2, 3, 4. This answer is also correct. So guys, now everyone got the concept of this one. How to find a degree of a particular vertex. Now in this only, if we have, this is an example of undirected graph, right? So if we are having a graph, having directions. So let's say A is pointing here, this 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 is pointing here, and this is pointing here. We have given direction to each edge, right? Yes. So when we will be encountering directed graph, at that time the degree of a vertex is calculated as in degree and out degree. So what is this in degree and out degree is? A, B, C, D, and degree. In degree is the number of incoming nodes to that vertex. Out degree means the number of outgoing nodes from that vertex. So when we consider A, here we can see we are having two edges. But in these two edges, one is incoming edge and one is outgoing edge. So the in degree of A would be 1, not 2, 1. Why? Because for this vertex, how many incoming edges are there? Only one incoming edge. So the in degree of A would be 1. Likewise, the out degree of A would also be 1 because from A only one one edge is going. So when it comes to B, in B there are two incoming edges. One is coming from A, one is coming from C. So the in degree of B would be 2. Sorry guys. So when it comes to out degree, from B only one edge is going. That's why the out degree of B would be 1. So guys, like this, I want you to uh, write first all the integers of CDE. Only integer of C, D and E. Integer of C is 2. Integer of D is 1. Integer of E is also 1. That is correct. Now write the integer of CDE. 1, 1, 2. So the out degree of C is 1. The out degree of D is also 1. The out degree of E is 2. Okay, from here. Okay. So guys, everyone got to know, right? How we will find out the degree of vertex. If it is an undirected graph, how we will find. If it is a directed graph, how we will find the integer and out degree. Guys, if you got the concept, just say got the concept. Got it? Yes. So now I will just write few concepts or patterns which are what we can say, which are asked in graph question. So in graph there is not like so much content to ask. If there are any questions also that can be solved using these particular patterns itself, each and every time you have to, by hook or like by directly or indirectly, they will be referring to use this concept itself. So when we say about concepts or when we say about patterns, at that time what comes to our mind? A template. So we can just create a template for each of these patterns and we can use it when according to the question. So we need to read the question, then we will find out, we will just have to find out in which pattern that question is, and then we have to remember the template of that particular pattern, and depending upon the question's requirement we have to change, modify that little bit, and we will be ready with the algorithm of it. That's it. For tree also we did the same thing, for stack also we did the same thing, for recursion also we did the same thing. So when everyone say, right, DSA is all about finding patterns, so whoever know patterns, they can clear DSA very easily. So here are few questions or the what we can say pattern topics which are always asked in graph. First one is traversal. So when it comes to traversal, you have to write how many, like the types of traversal, or find the path, like find all path. When we say all path, then we can use traversal. Next thing is when we have to search something. So they will provide us one node, and from that node we have to just search it where it is present, or it is present. Like they will give us a node. Let's take this example. Okay, they will give us this node, and they will give us this node. This is a path. So A to C is a path. Now what we have to consider, if we are traveling from A to C, what is our minimum distance? So let's say this one. So we have to here what was the question? We have to travel from A to D. So what is the minimum path? But in that question also they will insert something. Okay? We have to travel from A to D, but in between we have to visit B mandatorily. So at that time, what is the minimum path we will travel? So at that time, this path is not the answer. At that time, this path will become answer, because here we will cross through B also. We have to go from A to D, but for when in question they will be given that we have to uh, cross B also mandatorily. At that time, this will be our minimum path. When this will be in used in real case scenarios, in map, right? In map you will you'll get the from and you'll get the destination. It will show you the distance like this like 20 minutes or something, 12 minutes something. Later what you will do, there will be an option called add stops. So when you click add stop, here you can see C or something, B or something, A or something. They will show you how many wherever you have to stop. At that time, what it will do, you have to travel from your current destination, current location to destination location. But in that path, you have to add your this stop also. So basically, you have to add from you have to move from A to D, but in between you have to pass through B also. So if this is your shortest path, still you have to pass like this, right? So this very few like real world scenarios where this would be used. Okay, so traversal pattern. From just this one pattern, I have just mentioned 3 to 4 examples, 3 to 4 problems. There are n number of problems in traversal. Next one is path existence. So path existence also same thing. Path existence. Guys, I'm having a delay with this teaching part. That's why the typing speed and handwriting are uh, gone. Next one is cycle detection. When it's come to cycle detection, again we will be seeing our Floyd's algorithm. As if you don't remember, we solved this Floyd's algorithm in our arrays concept. We used the technique, two pointers, that too fast pointer and slow pointer. Right? If anyone remember it, the cycle detection problem, they would recognize it. So like this only it will happen when you will sit in interview, right? You need just get the question, you'll just see cycle detection or you'll just see Floyd's. This should hit your mind. We have solved this in a case. We will use two pointers, one fast pointer and slow pointer. We'll jump fast pointer 2 times. We'll jump slow pointer 1 time. If that matches, then cycle is present. If that doesn't match, then cycle is not present. So within 10 to 20 seconds, you got the approach how to solve it. Then later 1 minute you have to sit and write the structure and algorithm for it. After that, if your typing speed is fast, you can complete this question from scratch like 4 to 5 minutes. That's it. So this is the power of practice. Next one is topological sort. When we have to sort our tree, sort our graph depending upon the question. And our last one is connected components. So this is few patterns which are commonly used when we go through our graph questions. Okay, and I would like to add one more table here. These are the topics which you should cover, which you should must cover in graph. Okay, so if we, due to some reason or due to time complexity, if we didn't complete in this session, in this boot camp also, I would recommend you to practice at least these questions in graph. Okay, so we will try to complete everything. Connected components. Last one is connected components. Okay, we will try to cover, but you know, right? In 30 days, we are already in 24. We have to again see bit manipulation also. So there are few concepts. Next, first one is BFS DFS. This we will surely solve. Next one is topological sort. This one itself. Next one is Khan's algorithm. Next one is Dijitra's algorithm. Next one is Bellman Ford algorithms. Guys, this and all algorithms, right? These are very important from your interview point of view. In real world point, they will say that we will use this or all everything in real world point of view, and they will give you the scenarios. But in real world, we will be solving much more advanced level of algorithms. These are the fundamental algorithms, right? So you have to know the concept of these fundamental algorithms to just understand how we are using, how we can use, what are the real case scenarios. That's it. So most of the time they will ask you in interviews. So why they will ask you this kind of algorithms in interview is, let's consider an example of cycle detection. If they ask you the concept of cycle detection, or to say you they want you to test that if you know cycle detection or not. So at that time, how they will ask, they will say that will be giving you an array, and then that array have to test if there are cycle are present. Then they have to explain you, right? So why will interviewer waste that much time to explain you the question and then expect an answer from you? Rather, he will just say the name of algorithm. Do you know Bell-Bunford algorithm? If you say yes, he will say to explain. That's it. So for him, saying one word is very easy. And if you get the reference, if you got the whole algorithm by hearing just one word, Bellman Food, at that time it will show that how much dedicated you are, and how much time you have invested in learning DSC. So that's why most of the technical rounds they will ask you to solve algorithms. The famous algorithms is Digitax algorithm, Bellman Food, Khan's, and there are many of them. Floyd's, which we said. Okay. Oh, so Floyd's is next one. Floyd's, okay. Next one is MST with minimum spanning tree. That one we will solve. MST, MST minimum spanning tree. Okay, we will use this concept, and Krishkal's algorithm. So this one is also one of the famous algorithm. Next one is so connected components, strongly connected components. This is optional, but you can learn. Okay, this is also very good. So the thing is, when we go complex thing, right? Complex topics at that time, you have to see this type of things, algorithms, Floyd's algorithm, and go through YouTube, go through other free resources also. Try to learn as much as possible. So next, let's go to our next concept, which is graph representation. So we have seen how graph looks like this. A is connected to B, B is connected to C, C is connected to D. Like that we have seen. But how we exactly represent that in a code? Right? We can't just insert this diagram in a code. So we need something. In graph, okay, let me just erase this and copy paste nice looking graph. Let's take this one. So if this is our graph, we can represent it in two types. Okay, adjacency or adjacent. Okay, adjacent list or adjacency list. Next one is also adjacency matrix. So what is this? First, let's see this one. For most of our questions, we will solve using this one itself, adjacency list. But you guys need to understand this one also. Both are very easy, very straightforward. Okay. So list, you will be having a list. In list, what you will be having? You will be having all the vertices. So what is the vertex? First vertex is A. So basically, how we will get here is we will use a map, and in map first we will get the vertices, and then we will write the list of neighbors. We can call it as neighbors. Okay, this is just an example. This is just a structure I have written so that you understand it more easily. This is not the actual structure. Okay, so what we'll get? We'll get a vertex first. So we have written first vertex, and we will map it with the list of its neighbor, E and B, right? So E and B. Next, what we have to do? We have to get the next vertex, B. B, we will get A, E, and C. A, E, and C. Next, we will get for C. For C, B, E, and D. B, E, and D. Here the order is okay. You can, let's sort it out. You can just write it anyway. Anything, that's okay. E, C, E, C. Last one is the A, B, C, D. We will close it. So this is a representation of this particular graph in adjacency list manner. So let's see how we will represent it using a matrix. When we come to matrix, matrix means what? Like it will be having rows, it will be having columns. That is matrix. So we'll get all our vectors A, B, C, D, E. A, B, C, D, E. Initially, our all diagonals would be 0. So now what we will get? Our A is connected to E and B, right? So we will get E and B as 1, remaining 1, 0. Next we will go to B. B is connected to A, E, C. A, E, C, remaining is 0. C is connected to B, E, D. C is connected to B, E, D. Remaining one is 0. Arc D is connected to E and C. Arc D is connected to E, C. Remaining are 0. Arc E is connected to A, B, C, D. A, B, C, D. So this is a representation of this particular tree in adjacency matrix format. So guys, everyone got it right? How we can represent our graph? Okay. So if you got it, then we will move to our first concept, which is DFS. So this is in like you have to concentrate and learn it. Okay, this is a little bit confusing, but see, if you understood it, it is very, very easy. You are standing here. I'll just give you a brief example of BFS and DFS both. Then we will go to DFS. Then we will see algorithm. Okay. First, I'll give an overview of DFS and BFS. So suppose if you are standing in a room, here you are having 4 doors. So this is one more room. Here you are having one more room. Okay. So suppose this one you are having. So what you can do is one method, what you can do is you can drop something here. Okay, so just recognize you are starting from here. What you will do, you go to this room, and then you'll drop something, and you'll go to this room. You'll drop something here. There are no other doors, right? At that time, what you'll go, you will return back and go to here again. You have it dropped here, right? Something, so that's why you will not see. Let me just say it again. So basically, let's give number to this: 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are rooms. You are get a room number 5. You have to write the rooms number wherever you have gone, right? So you are starting from 5. You will drop something and you will write it in your notes. You go here. You will be at 4. At that time, what you will drop something and go to the next part. This is 7. So you go here. You will get 7. Here you reach dead end. At that time, what you will do? You will give it back. You have already dropped, so you have already dropped it, right? So you will not get anything. You go to your next option. Next option, you get 1. And here also you don't have anything. So what you'll do, you'll give it back here. Okay, when you give it back here, oh shit, 1. Okay, what you have done, you have dropped, you have visited this 4 rooms. Next, what you'll do, you'll go to your next option. What is your next option? Let's say this is your next option. So you'll go here. Then you'll get it. You will drop something and get it. Next, you are having no other option. At that time, you'll return back. So basically, this one you will do it, right? So what it is, you will visit a room, then visit another room till you reach end. Okay, this is one of the method you will do. What's the one more method is, first you'll go to this room. Okay, next what you'll do, you'll come back. First you'll go here, you'll drop something, you'll come back. What next you'll do, go here, you'll drop something, you'll come back. Next what you'll do, you'll go here, drop something, come back. Next you'll go here, drop something, come back. Next what you'll do, next you'll go to our first path and then go to our next path. Again you'll drop something, come back. So basically there are 2 ways, 2 approaches. The first approach which I said, right, you will visit a room and then go to the you'll just continue it till you get a dead end. So that approach is called as depth first search approach, DFS approach. So if we are having a node C, D, what you do, you go first. I should not write. No, you'll go first here, next you'll go here, next you'll go here. Okay, if it is connected like this, what you'll go, you go here, next you'll go here, next you'll go here, next you'll go here. Like this, you will traverse till you reach. Suppose here you are having another one. Here you are having another one. You are having another one. So first you opted this approach, this room, this path. Then you will continue this path. Here also, if you want to approach this, you have already visited it, right? So you will not go to visited one. You approach next one, this one. Next you will go to this one. Now what happened? Now it's dead end. At that time what will you do? You will get back and go to your next option, this one. So this approach is called as DFS. Whereas in BFS, what you will do? You will go to this one, you'll come back, you'll go to this one, you'll come back, you'll go to this one, you'll come back, you'll go to this one. So when every first level is cleared, then what you'll do, you'll increase your level and go to level 2. In level 2, you'll go here, you'll come explore this, you'll go here, there is nothing, you'll go here, there is nothing. So level 2 is clear. And next what you'll do, you'll go to level 3. This, and come back. Next, this, and come back. So this approach is called as BFS. It's like waves, right? So when you will be going, you'll encounter every possible thing which you can, then you will move one step. Next, every possible thing, then you will one step. So this wave approach is called as BFS. DFS means you'll just guess your intrusive thought and go to a particular path till you reach the dead end. If you reach your destination, that's it, final. If you didn't reach the destination, again you will come and reverse back and try another approach. So this is DFS, this is BFS. I hope I have given you a brief introduction about the approaches, like what is DFS, what is BFS. Okay, in BFS, we'll just take the reference of what we have did for previous also. In tree, we will just go and see what we did. We used our queue, right? We used the key. Here it is. The same approach we will use for BFS in graph also. So here what we did, we initialized the queue and we followed our condition. What is our condition? When a node enters in a queue, we have to delete that node, print that node and add its child node. So what's the one word which would change in graph is child node is child node. We will change it to modify it to neighbor node. That's it. So basically we will put our first node in a queue. Then what we'll do, we have to delete that node, print that node, and we will add neighbor's node of that particular node in a queue. So then we will get a BFS. We will understand it by a simple example. Let's take this example, this graph example, okay? So let's consider we are solving a BFS of A. Okay, this is our first node. We will be having a queue. What we have to do, first we will add our A to a node. When we add our first node, when we are having elements in a queue, what we'll do, we will delete that and print that thing. Next what we'll do, we will add the neighbor node. What are the neighbor node of A? E and B. So we will delete our A and we will add E, B to our queue. Next what we should do, we will again delete it. We will delete it, we will be having E and add neighbors of E and B. So what are neighbors of E and B? What are neighbors of E? We have just removed E. What are neighbors of E? D, C, B. D, C. We have already added B. We have already visited B, right? So after this, we have to visit it also. So when we print, we will convert it as visited. We have visited this. We have visited this. Next, what we should do? B is also visit. When we write any node here, right, we will convert it into visited. Visited, visited, visited. Basically, we have visited everything. When we pop E, we should add D and C. Then everything would be shifted B would be shifted here, D here, C here. D here, C here. Again, what you will do? Again, you will remove pop element from a queue. B would be removed. We need to add adjacent of B. Unvisited adjacent. We are not having any unvisited adjacent. We'll just remove it. When we shift it, it will be D, and here we will be having C. Next, we will remove D. We will have D here. We will remove C. We will have C here. So this is basically our BFS. So A, E, B, D, C. So if it was in a tree structure also, we in BFS what we'll do, we'll go level wise, right? So level wise, A, E, B, D, C, A, E, B, D, C. This is BFS. I think everyone got it.